Let me start by saying thank you to the IHES. I wrote my PhD here with Dennis Sullivan in the 1980s, and it's a great honor to be back again, and a great pleasure for this month. And it's equally an honor to be part of this celebration of Maxime's 60th birthday and his tremendous mathematical originality. So I'm going to talk today on a subject that blends several elementary and more advanced mathematical topics. I'm not going to try to give detailed attributions, but there's a lot of people involved, going back to Weil for heights and Manin and Birch for modular symbols, and all the way through. One thing I want to draw your attention to is the work of Kontsevich and Zorich, which a few years ago, more than a few now, really rekindled interest in this subject in a phenomenal way, and was kind of pivotal in the current renaissance of the theory of interval exchange maps, billiards, curves in moduli space, and so on. And the most recent contributions, which I'll briefly mention, were made just a few months ago by Frank Caligari. Okay, so billiards. So like most people in this conference, I want to talk about mathematical physics. So for me, the physical system will be a billiard ball moving around in a polygonal table. And in fact, the case of a square is, of course, very well understood, but the case of a billiard ball moving in a regular pentagon is already quite sophisticated, and there are even unsolved problems in this area. And for the purposes of this talk, I'll just deal with billiards in regular polygons. One thing we know, which is a little bit surprising, it's hard to find an elementary proof of this, is that there's a dense set of slopes such that the billiard path that begins with that slope is periodic. It comes back to where it started.
Independent of point?
And it turns out that once there's one periodic path, all the paths that begin with that slope, no matter where they start, are periodic. So the slopes can be categorized and put into two classes, periodic and non-periodic. And so it's interesting to ask then, which are the periodic slopes? And also, how do these periodic trajectories behave? So first, let me show you some experiments. This is even experimental physics. So here's the simplest periodic billiard path in the pentagon. Is this inscribed pentagram? As you can imagine, this is corresponding to the slope of 0, or maybe better, this slope here, which is parallel to this edge here. I'll call that slope S. And this particular trajectory comes back to itself after hitting the sides 5 times. And I really, this is an elementary experiment to carry out, and I really encourage people to do it, because you immediately see something that I found quite surprising when I did it. So you change the slope a little bit. So I tried just multiplying it by 4, and it stayed periodic. But the length of the trajectory went up quite a bit. It takes 469 bounces before the path comes back to where it starts. And if you multiply by a well-chosen larger integer, well, let's first start with 20. The trajectory looks almost dense. It's almost completely black here. It takes more than 2,000 reflections off the sides before it returns to where it started. And I won't draw the picture for 6, 7, 6, 5 times S, because it looks exactly the same. But it takes about 10 to the 25 bounces before it returns. So it's interesting that these slopes, these integer multiples of S, experimentally all give periodic slopes, but it becomes harder and harder to observe. So when you plug in this integer, a naive computer simulation will never reveal that it's periodic, or rather, it will say it's periodic, but it's because of a numerical error.
So this is approximate, the last?
No, well, I have the exact number. I didn't write it down. But that's another good question, which I'm not going to answer right now. How did I compute that number?
But there are computers on the computer.
Sorry?
You can do this on the computer.
10 to the 25? I don't think so. Okay, so let's go on to a general theorem now. So in fact, we know what the periodic slopes are in the pentagon. I had this initial slope S, which is the slope of one of the sides. And in fact, the periodic slopes coincide with multiples of those by elements of the field Q adjoin root 5. And moreover, there's an estimate for the length of the trajectory. And since it gets so large, I'll make an estimate for the log of the length. And the log of the length can be bounded in terms of the height of the slope, the arithmetic height of this number in Q adjoin square root of 5. But it's the square of the height. And it's that square that reflects the fact that the length of the trajectory grows much faster than our description of the slope of the trajectory. So if you don't know what the height is, just imagine that for an integer, the height of n is its logarithm. And so what this means is if you put in an n-digit number, you might easily have a trajectory that takes 10 to the n squared reflections before it closes. And in fact, this exponent 2 is sharp, as you would guess looking at some of the experiments. Okay.
Lengths, but in fact you count the number of reflections. Is it easily related to the actual lengths or the...
It is related, but it's in a complex way. They're comparable. They can both be computed. Okay, so now let me say what underlies this, the fact that we can understand the dynamics in of billiards in a pentagon. It's all based on renormalization. Rather than saying in detail what renormalization is, let me say the theorem that comes out of it, which is due to Veach from the 1990s. So what Veach showed is that the periodic slopes for billiards in a regular pentagon, and this generalizes to other n-gons, they correspond to the cusps of a certain triangle group, which I'll call delta 5, contained in SL2R, a classical triangle group acting on the upper half plane. So to understand what the periodic slopes are, we now can forget the physics and the billiards and just be mathematicians and try to study this discrete group. And so here's a picture of that group. There's a fundamental domain which looks a little bit like the fundamental domain for SL2Z. And in fact, this element that fixes I that you know from SL2Z, that's in the group. But here there's a point where the stabilizer has order 5. That's this R here. So this is called the 2 5 infinity triangle group because the quotient Riemann surface is an orbifold with signature 2 5 infinity. We'll draw a picture in a moment. So anyway, this is a very concrete group. We can write down the matrices for it. But let me first tell you what renormalization is good for. So it turns out that up to the action of this renormalization group, there is only one type of periodic billiard in the pentagon. They're all the same up to this renormalization action, whatever that means exactly. And this has to do with the fact that when you take the cusp of the quotient Riemann surface for the triangle group delta 5, well, when you form this quotient Riemann surface, here's a picture of it. It's a 2 5 infinity orbifold. It just has one cusp. And in other words, all of the points that are fixed by parabolic elements on the boundary of the upper half plane, they all lie in a single orbit of the group. And this is really the secret and power of renormalization, is to understand billiards in the pentagon. In some more sophisticated viewpoint, there's really only one periodic trajectory to understand. But then that just hides the difficulty of understanding inside this renormalization group, delta 5. Okay, so let's talk about this triangle group then a little. So one thing I'd like to add to the perspective is that this triangle group, although it's a lattice in SL2R, it can also be thought of as a thin group in SL2R cross SL2R. And that perspective will be critical for the discussion going forward. So just to introduce some notation, as you can guess, if you're doing the pentagon, this field K adjoin root 5, which has already been mentioned, arises. The this ring of integers, which is generated by the golden ratio, gamma, is also important. So this is some notation. And then the full group of matrices with entries in this ring of integers is an arithmetic group. But you shouldn't think of it in SL2R. You should use the two places of this field to embed it in SL2R squared. It's an arithmetic lattice in that product. On the other hand, our group, our triangle group, does have matrix entries in this ring of integers, but it's of infinite index in this non-arithmetic group. So it is itself a non-arithmetic group. And non-arithmetic groups are hard to understand. So what do I mean by that? So first, here are the generators of the group. That's not so bad. Here they are acting geometrically. There's the 2, 5 infinity triangle. But if I ask you, for example, which numbers can occur as matrix entries of some element in this group? Or what are the possible columns of matrices in this group? Or where are the cusps of this group? I've already hinted that we'll know the answer to that. In general, for a non-arithmetic group, all of these questions are very difficult. But not with this group, some of them. So the first statement is the cusps of this triangle group coincide with everything they could possibly be. They're just Q adjoin root 5 union the point at infinity. And even better, these cusps satisfy what I'll call quadratic height bounds, which has something to do with the group. And rather than define that, we'll see in corollaries of this theorem what it means. So let me just describe what this theorem says geometrically. So how would you construct the cusps of this delta 5 group geometrically? So one way is to notice that if we think of the region above this line as a circle, that there's 5 circles packed around this green point. 1, 2, 3, 4, 5. And they're packed symmetrically in the sense that there's a Mobius transformation that cyclically permutes them. And then if you look down here between any two of these circles, there's a canonical way to put in 3 more. And then between any two of those, there's a canonical way to put in 3 more. So there's lots and lots of cycles, each consisting of 5 circles. And the theorem is that the bases of these circles eventually touch every point in the field Q adjoin root 5. You can easily show the bases lie in Q adjoin root 5, but they eventually hit every point. Okay, so that's the statement of the theorem about delta 5. And it can also be stated in terms of continued fractions. So here's something I like to call the golden fraction of a number. So we work in this field Q adjoin root 5. I put the generator to be the golden ratio because I'm going to use that in defining continued fractions. So given a number in this field, I first write it as an integral multiple of gamma. So all these coefficients are integers. And maybe I try to make what's left over pretty small. And then I take the reciprocal of what's left over and I try to write it as an integral model of gamma and so on. So this is exactly like the traditional continued fraction expansion of a real number. But I put a gamma in front of every one of these integers. And then the theorem is that...
Are the AIs positive after 1?
No, I didn't say they have to be positive.
Maybe the last one is not 0 yet.
But they should be integers. So just to make this statement robust, I'm not going to add more conventions to what they should be. And the statement is that every element of Q adjoin gamma can be expressed as a finite continued fraction. This process, forming the continued fraction for S, which you can easily program, eventually terminates no matter what element of this field you start with. And then the height bounds make this effective. They actually make this into an algorithm. They tell you how long you have to wait for the algorithm to terminate in terms of the height of the number you're expanding. So for example, n here, the length of the continued fraction is bounded in terms of the height. These integers ai are bounded in terms of the height. And that's
this decomposition.
It could be made unique by adopting some conventions. I'm not going to bother Okay, so the statement is everything can be expressed in this way, in such a way that that n and ai are bounded by the height.
Gamma satisfies the quadratic equation, so that's finite.
Gamma is a domain.
Gamma satisfies a quadratic equation, yes?
And because of that, it's finite. The continued fraction.
No, not at all. So notice this is first, so first, if I were to expand this as a traditional continued fraction with gamma here, it would be infinite but periodic. Yeah? But this is very different because I'm only using integers here, even though I'm in this quadratic extension of Q. Okay, so this is a fairly deep theorem. Okay, so and in fact, to explain the theorem in more detail and a conceptual proof of it, I need to introduce some more geometry. So let me just say, without further elaboration, that what makes this theorem of Veitch work is the fact that there's associated to this triangle group, there's a natural map from the quotient of the upper half plane by this group, which I'll call V, into the moduli space of Riemann surfaces of genus 2. And you can further follow this map by taking its Jacobian to get a map into the abelian varieties of rank 2. And remarkably, it turns out that along this curve V in moduli space, the Jacobians always have real multiplication. And I'll elaborate what that means in a moment. It means there's special endomorphisms for the Jacobian of xv. And even more remarkably, there's a hyperbolic metric on V, and there's a Teichmuller metric on M2. And this map is totally geodesic for that, for those two metrics. And there's a Schwarz lemma that says that any curve sitting in moduli space gives a contraction from its intrinsic hyperbolic metric to its extrinsic Teichmuller metric. But in this case, it's an isometry. So this is sort of an extremal curve in moduli space, and the Jacobians have remarkable properties, which means that this map to the moduli space of abelian varieties factors through a map to a Hilbert modular surface. This Hilbert modular surface parameterizes principally polarized abelian varieties with real multiplication by the field Q adjoining root 5, or more precisely by the ring of integers in that field. So this Hilbert modular surface is kind of intervening in the picture between moduli space, which is kind of tricky to understand, and our group delta 5. And you'll notice this is sort of a geometric lifting of the inclusion of delta 5 as a thin group into SL2OK. That arises by thinking of V as a curve on the Hilbert modular surface associated to this arithmetic group. And V is a totally geodesic curve here, but not for the usual Riemannian metric on this Hilbert modular surface, for its Kobayashi metric. So I call it a geodesic curve, but for those who know, it's Kobayashi geodesic, not Riemannian geodesic. Okay, so what this suggests, this factorization, is that maybe the fact that these billiards have periodic trajectories and they can be controlled doesn't have much to do with the fact that V maps into moduli space. Maybe it has more to do with the fact that V sits on a Hilbert modular surface. So I want to describe a result which justifies that intuition. It will apply in the quadratic case, like Q adjoin gamma. So assume K is a real quadratic field, then the theorem is that the cusps of every geodesic curve on this Hilbert modular surface coincide with P1 of the underlying field. In other words, everything that could be a cusp is a cusp. These are, so to speak, the cusps of the Hilbert modular surface itself, and this curve represents every cusp, and moreover, in some technical way, these quadratic height bounds go along for the ride.
What is delta?
Delta is, there should be a subscript of there was a subscript of 5 there before. So delta is a discrete group acting on the hyperbolic plane. So V is a curve, which it's of higher genus, so it's hyperbolic, so it can be expressed as the quotient of the upper half plane by a discrete group. And in fact, because this is a geodesic curve, this discrete group can be taken to be a subgroup of SL2OK.
So what is the quadratic height bound? Does it relate the height of...
I already said what it was, offer in specific examples. That's all. I won't elaborate further. It has to do with controlling the continued fraction.
But what is the connection between delta and k?
Oh, so nothing. To start out with, there's no connection between delta and k, but there's this word geodesic here. So remember, this curve has to be geodesically embedded from one space to the other, and that implies that delta can be realized as a subgroup of SL2OK. Okay, so it's a consequence of the hypothesis that delta, which looks random at first, is in fact a thin subgroup of SL2OK, just as in the billiard case. So the billiards have disappeared and the triangle group has disappeared, but the results on billiards and the cusps of delta n follow. At least in the case of the pentagon and the octagon and the 12-gon, the n-gons that have something to do with quadratic fields. Okay, so I want to just give a hint of the mathematics that lies behind this theorem. It has to do with heights. And so here's the idea. So I'm going to talk about descent, and there are people in the audience who have very sophisticated understanding about what descent means. That's not me. So descent means it's a la Fermat. You're trying to prove something about the solutions to an equation. You start with a purported solution, you do some manipulation, you get a smaller solution. And then you keep going, and from this, maybe by contradiction, you show there's no solution, or you deduce something about the solutions that there are. So to show that a continued fraction for a point in P1 of k terminates, the classical way would be to show there's some measure of the complexity of the number you're trying to expand, which decreases at each step of the continued fraction algorithm. And if that's true, then you can use that to give a proof that the continued fraction terminates. But it's quite awkward to find this height, and it's quite non-conceptual how the proof came about. So I'm going to try to give a more modern approach. So rather than trying to show a continued fraction terminates, what I'm trying to show, and it's really equivalent, is that a geodesic, hyperbolic geodesic, on this special curve V in this Hilbert modular surface, that I want to show that it heads towards a cusp in P1 of k. And this cusp will be described by a particular point on the projective line. And I'm going to do this by showing that the height of x, as seen from the abelian variety corresponding to this point in xk, tends to 0 as A moves along this geodesic gamma. So to set this up, what I need is a way to measure the size of an element on the projective line using an abelian variety with real multiplication by k. And I'm just going to give you a glimpse of how that works. But to sum up why I wanted to develop this approach, this is kind of a discrete method, and you have to be very clever to find h. And this is a continuous method because we're just moving along this geodesic, and the h is very natural. It just drops out, and you just see if it works or not. Okay, so to describe this height, let me just remind you something about the classical height on the projective space of dimension n over, well, any number field k. So what you do is you take a point in projective space, you write it in homogeneous coordinates. So these numbers x0 through xn are elements of k. And then you take the product over all the places of your field, including the finite places, of the maximum of each coordinate with respect to the given place, the given valuation. And this product is always greater than or equal to 1 by the product formula. And even more, this product doesn't depend on the choice of these representatives. And that's the classical and fairly canonical height for points on on projective space. Well, I'm only going to need this on P1. Now, as an analyst, I don't really like doing these valuations at the finite places, but I do know what an integer is. So what I prefer to do is the following. I say, here's how I compute the height. I just take the infinite places of the field, the different embeddings into the real or complex numbers, and I use those valuations. I just peel off those terms in this product. Those are things that have geometric significance. But then I add the requirement that I'm not expressing x's in homogeneous coordinates using elements of the field. I require that I'm using integers, algebraic integers in the field. And then I try to make this expression as simple as possible. And that height is comparable to this height. But the point I want to draw your attention to is I only need to know the infinite places and what it means to be an integer to compute this height. And those two properties transport nicely to the setting of abelian varieties. So not to go into too much detail, but what real multiplication means is we have a polarized abelian variety, a totally real number field. Its degree is the same as the dimension of the abelian variety. And this field acts by endomorphisms on A, at least after you tensor with Q, and it should act self-adjointly. That's a technical condition. Now, once you have this action of K on this abelian variety A, then it acts on the cohomology of this variety, and therefore H1 of A, which would usually be Q to the 2G, where G is the rank of A, becomes a two-dimensional vector space over K. And so there's a projective line canonically attached to this variety. It's not quite the abstract projective line. It's really the space of K lines in the rational cohomology of X considered as a vector space over K. And this is where we're going to introduce our height. And by the way, we also get a basis of eigenforms for the action of K. Those sit in the 1 forms on A. And they're indexed by the infinite places of the field. Okay, so using this data, one can define what I call the Hodge height of a point in P1 of K. And so here's how it works. So what you do is you take an element of the integral cohomology of A. So you just take a loop on your abelian variety that represents this K line. So it lies on a particular K line in the rational cohomology. So notice I have to know what an integral point is, but not much more. And then I integrate these eigenforms over that cycle. So I look what the periods are of the eigenforms over this cycle. They're thrown in 1 over G for good measure. And then I try to choose this cycle C, this integral cycle, to make this product as small as possible. And so you could think of this as I'm taking the integral representations of a point on this projective line, and I'm taking the product of their Hodge valuations at the point at infinity. In fact, you could think of this as the Hodge norm of the projection of C to one of the eigenspaces for the action of K.
So I don't understand. So this is it's an integral of a real curve of a.
Yep, it's just a loop. It's a period. Yes, absolutely. It's a period. It's a period.
What does it mean? Subscript nu.
Okay, so this went by fast. So when K acts on this abelian variety, it also acts on the space of holomorphic 1 forms on the variety. And you can diagonalize that action. And you get one eigenform. So you think of the action as being generated by one endomorphism of A. This endomorphism has different eigenvalues. They're all Galois conjugate. Each one has its own eigenform. Generates the eigenvector in the space of holomorphic 1 forms. And I'm using those eigenforms to measure the size of this curve. I'm looking at their periods. Okay? Thank you, Pavel. Good question. I meant to go almost as fast as Yuri. Okay, so let me just say then what happens for Hilbert modular surfaces, and it doesn't really matter if you understood what went before. The main thing is that the height that this height is comparable to the ordinary height on a projective line. And the ordinary height is bounded below. It's bounded below by 1 in the usual normalization. So this height is bounded below as long as A stays in a compact set. On the other hand, it's bounded above by the periods of these two eigenforms over the given curve. And it turns out that what happens is that if you move along an appropriate geodesic on this curve V in xk, you can force the first term to go to 0 exponentially fast. And then there's a Schwarz lemma argument that says the second term grows slower than the first term contracts. And therefore, this quantity goes to 0. And that forces the height to go to 0. But the only way that can happen is if the abelian variety A is going to infinity in the Hilbert modular surface. And that means that, that in fact, gamma converged to a cusp in P1 of k. OK, so that's a sketch. And that's the most elaborate proof I'll sketch in this talk of the proof of these theorems that can be stated in an elementary way for billiards in the regular pentagon. OK, so I have to confess, this only works for quadratic fields. It only works for Hilbert modular surfaces. And you saw why. I have these two competing terms. One goes to 0 exponentially fast. The other goes to 0 somewhat slower. But if there were two terms going to 0 somewhat slower, they might together grow like e to the 1.5 times t, and then they would beat the first term. So this argument doesn't work beyond quadratic fields. And in fact, we seem to be brushing very close to some kind of undecidable problem when we try to extend this theory, for example, even to cubic fields. So let me do this the way they do in computer science. So in computer science, problems are always described in capital letters, like clique. This one I'm going to call cusp. And each instance of this problem depends on an integer n. So cusp of n is the following. You're given a slope in the field k, and you have to decide if it's a cusp of the n triangle group. So this is the 2n infinity triangle group, generalizing the group delta 5 that occurred earlier. So the question is there an n equals 7, 9, 11, etc.? These are the ones that are open, such that this problem is undecidable. In other words, such that there is no algorithm to solve this problem. There's no fixed algorithm. You fix n, you have to write your program, and then it has to work for every s that you input. Now, of course, if it were true in these cases that every slope in the field were a cusp, then there would be such an algorithm. In these cases, some slopes are cusps and some are not. And the question is, can we decide which are which? And it's open already for n is 7. When n is 7, we have a cubic number field. And we're discussing billiards in a heptagon. How different could this be? Here's the obvious billiard of length 7. And here's a somewhat less obvious billiard, which has a very simple description. And it's a periodic trajectory, but its length is 10 to the 40. Now, how did I compute this length? What I did was I applied some continued fraction algorithm to this number, and lo and behold, it terminated. But it was after quite a few steps. And there's no known way to test for periodicity of billiards. What we can do is we can prove a billiard is periodic if it is periodic, and we're willing to wait a very long time. But we don't know any good ways of proving given slopes are not periodic. And as a consequence, this problem might really be undecidable. Yes?
The length of the continued fraction was not 10 to the 40. You would not have computed that, right?
The length of the continued fraction is not 10 to the 40. So remember when the Fibonacci numbers grow exponentially fast. And they're related to 1 over 1 plus 1 over, right? So you go n terms and you get the nth Fibonacci number, which is exponentially large, like e to the n. So the length of the continued fraction is 40, shall we say.
What is k here?
So k is a cubic number field. Did I write it down somewhere? It's, sorry. It's q adjoining cosine 2 pi over 7.
But how is it related to the Fuchsian group, for example?
It's the trace field. It's the invariant trace field or the trace field. They're the same in this case. Yeah. There's something 7y going on here. 2 cosine pi over 5 is essentially the golden mean. This has to do with q cosine pi over 7. Okay, so let's move on. Here's my next problem, and I'm going to be even briefer about this. I just want to hint that there's some other objects that arise in number theory and other settings that are related to elementary questions in billiards. So once we know there's lots of periodic trajectories, we can ask, how are they distributed? How do they behave? What do they look like inside of our pentagon? Now Veach proved that if you take a slope that's not periodic, then the billiard trajectory is uniformly distributed in the pentagon. In particular, it's dense. And so you might think that long periodic trajectories should become more and more dense. But this is definitely not true, and Davis Liliev drew attention to this already in the pentagon. There's a trajectory which leaves a hole in the middle, and you can make this trajectory longer and longer if you're clever, and that hole never goes away. So long trajectories don't have to be equidistributed. And they wondered, is the set of measures you get by taking limits of these longer and longer trajectories, maybe it's a Cantor set. They had a tree-like structure in their discussion, and it looked like there might be sort of a Cantor set of limit measures. And these measures describe the scarring of billiards on the billiard table in the language of physics.
So measure is the time that the particle spends in a particular set. Is that what?
That's what equidistribution means. It's proportional to the area of the set. Yeah. But you can just think dense. I mean, even the topological assertion is false for long periodic billiards. So, the result I want to mention is the following. Actually, you don't get a Cantor set of measures. You get a countable set of measures, of limit measures, when you take these longer and longer trajectories. And this countable set is homeomorphic to the countable ordinal omega to the omega plus 1. So there's a nice analysis of what these measures are. And as I say, this describes scarring. It describes the closure of the ergodic measures for this billiards. It can be computed exactly. So here, if you don't know what omega to the omega is, let me just give you an idea. Here you can see these are lots of little dots. And these dots accumulate somewhere. When you have a bunch of dots accumulating somewhere, that's omega. When you have accumulations of accumulation points, that's omega squared. And so you can imagine what omega to the omega is. You have all of that. But as you take more and more derivations, you eventually converge to the uniform measure. And remarkably, this set of measures has a natural semi-group structure, which is not at all obvious from the description I just gave of it. And this also sheds information on the matrix entries in this group, delta 5, which I said were very elusive. And this structure comes from a theory of modular symbols. So let me just say what this theory is, because it's very simple and it goes back already to Birch and others. So when you have a finite volume hyperbolic surface with cusps, there's lots of geodesics that start in a cusp, spin around, and then eventually exit a different cusp, or possibly the same cusp. And once you have one of those geodesics, why not start again in that cusp, re-enter the surface, go around, exit a different cusp. So you can sort of take the category generated with the category with objects, the cusps, with morphisms, these chains of geodesics joining one cusp to the next. And that's what I call a modular symbol for this cusp surface. And it turns out the space of modular symbols carries a natural topology. As this geodesic, which joins these two cusps, if it goes deeper and deeper into this third cusp here, then in the limit, it converges to a composition of two geodesics, one which goes into this cusp and then comes back again and goes to that one. And the space of these modular symbols is homeomorphic to omega to the omega. And that sort of explains where the structure on the space of invariant measures comes from. Okay. Now the third topic blends together some more arithmetic properties, combinatorics, congruence, and chaos. Let me just tell you what the combinatorial feature is. So let's do a more detailed study of the pentagon. It's amazing how rich the pentagon is. So if you have a periodic slope, like slope 0, you can start your trajectory, as Maxime said. Let's talk about where we start our trajectory. So a good place to start your trajectory is the midpoint of an edge. And there's many reasons why this is a good point. In some further discussion, it corresponds to the Weierstrass points on an associated Riemann surface. But let's just speak naively. You start your trajectory with a given slope at this midpoint, or maybe you start at this midpoint. Oh, look, you get a different figure. Here you got an inscribed pentagon. Here you got an inscribed pentagram, a star. Here, if you move at slope 0, you run into a vertex. You actually skim along the edge and go bang into that red vertex in either direction. I call that a vertex connection. We'll see a more visual demonstration of that in the next example. And then you see, as you move around, keep moving the midpoint around, you see the same picture again that you saw for the first 2 steps. So somehow there's this distinguished trajectory which gives a vertex connection. And indeed, if we try a different slope, here's another vertex connection coming from this edge midpoint. And as we move the edge midpoint to the right or left of the one that gives the vertex connection, we see the same trajectories up to rotation. Here's another one that gives a very simple vertex connection and some more complicated trajectories. So another question you can ask is, if I give you the slope, can you predict the midpoint that's going to give a vertex connection? So the first theorem is, for every periodic slope, there is an edge midpoint that gives a vertex connection. Which one is it? So the theorem is that this can be computed in a very succinct way. You take your slope S, and there's a way to use it to define a point on the projective line over the ring of integers mod 2. And the desired midpoint MK gives the vertex connection exactly when that slope mod 2 coincides with the 5th root of unity to the kth power reduced mod 2. Okay, so there's a sort of congruence property that allows one to determine where this vertex connection is. So then when this kind of thing happens, I say that the location of the vertex connection is a congruence invariant. It can be determined without doing much computation. You just reduce the slope mod 2, so to speak. So I proved this for 5, and then I proved it for 7, and then I proved it for all odd numbers, and then I proved it for 8, and the proof was a little different. And I proved it for 10, and then I tried to prove it for 12, and I couldn't prove it. And so let me show you a graph of something interesting. So let's just suppose the slope is an integer, 0, 1, 2, 3, and so on. And so suppose the slope is an integer, and given an integer, I draw the billiards at that slope, that integral slope, and I look at where the edge midpoint is. Now, in the previous cases, this number k would be a periodic function of t, because it only depends on some congruence property of t reduced mod 2. Anyway, I'm going to just check the parity of k. So I'm going to raise -1 to the power of this integer k. And then I'm going to use that to generate a walk on the integers. Namely, I'm going to step to the right or the left, depending on the parity of this distinguished edge midpoint, the one I'm trying to predict, the one that gives a vertex connection. And what I see is something that looks indistinguishable from a random walk. So this gave a lot of credence to the statement that the location of the vertex connection is not a congruence invariant when n is equal to 12. And in fact, that's true, but there's obviously much more going on here. For example, one could ask if there's a central limit theorem, etc., but we don't even know if the mean of this process tends to 0, let alone the variation or anything like that. But all evidence is that hidden in billiards in a regular 12-gon is an arithmetic mechanism that generates an instance of a random walk. Okay, and I'll just say briefly that a good way to approach this question is, well, we have this thin group. It's of infinite index in SL2O. But if we take the profinite completion of OK, and then take SL2 of that, and then we take the closure of delta in then, so we do go to the sort of adelic perspective, then this group has finite index in this group. And actually, all of this congruence condition discussion has to do with determining what this closure is. So we can just ask, and this is a question that makes sense for every n, and in fact for every thin group and every reasonable arithmetic group, what is the profinite closure or the adelic closure of that thin group? And the answer is Frank Caligari knows. So I won't say in detail what it is, but I was able to prove enough about it to show that it doesn't work for n equals 12. And in fact, the complete solution to this problem for this sequence of triangle groups was computed by Frank Caligari. That's very, very recent work. So as a corollary, in fact, we know now when the location of the vertex connection is a congruence invariant. And there's these cases you have to rule out when n is 0 mod 4, like 12. But powers of 2 work. OK. So those were 3 excursions into the theory of billiards. And it's a little warm. It's after lunch. You can, if you're just waking up, here's a new discussion that begins ab ovo. It's a complément, as it's called in French.
On the previous slide, so the relationship with the constructible, these numbers occur with a constructible by à la règle et au compas numbers.
I know what you mean by constructible numbers, but I don't think there's a relation that I know. OK, so let me go. This is enough about polygons. I'm going to talk just about triangles now. So of course, we're all familiar with Euclidean triangles, but there are also hyperbolic triangles and spherical triangles. And when the angles are, say, pi over n, the reflections in the sides of these triangles can generate nice tiling. So one of the classical examples is the 2, 3, 7 triangle group. This is a compact triangle. There's no cusp anymore. There's no infinity here. And this triangle generates, by reflection through its sides, this beautiful tiling of the hyperbolic disk. And if you zoom in on one of these triangles, you can see the angles are pi over 7. One of them is 90 degrees, pi over 2, and the last one is pi over 3. Of course, this has a defect, which is why it's a hyperbolic triangle. You'd have to have a 6 here for it to be Euclidean. OK, so these are the kind of triangle groups I want to consider. But I also want to consider Euclidean triangles, and I also want to consider spherical triangles. Now, why don't we take all these different triangles and put them together into one space, independent of whether their angles are multiples of pi by rational numbers, independent of whether they're spherical or Euclidean. So if you do that, you just get a torus, because a triangle is specified by 3 angles. And this torus can be nicely subdivided into regions where that triangle is spherical, where it's Euclidean, and where it's hyperbolic. So here's something interesting. When all of these angles are rational multiples of pi, well, we can think of them as corresponding to roots of unity. But equivalently, they're torsion points on this torus. In any case, they have a Galois orbit, which you can write naively. If it's torsion of order n, you just take the invertible elements in Z mod n and multiply them by a. They're all the different generators for the cyclic group generated by a. We call that the Galois orbit of a. If a were really a list of 3 roots of unity, this would be its ordinary Galois orbit.
But Euclidean triangle do modular scaling.
Sorry?
Euclidean modular scaling.
Yeah, modular scaling. Thank you. There's lots of nuances here that I'm going to sweep under the rug. But you always will have them right, Pavel. OK, so we think of the AIs as roots of 1, talk about this Galois orbit, and now we can ask the following question. We define what I call the ramification density. So you give me 3 rational angles, and I look at the number of spherical triangles in its Galois orbit divided by the whole Galois orbit. And there's a reason this is called the ramification density. It has to do with ramification in quaternion algebra, so you don't need to go into that. This is a very naive and simple idea. You move the roots of unity around and you see if the triangle is hyperbolic, spherical, or Euclidean. If it starts out hyperbolic, then all of the Galois conjugates are either hyperbolic or spherical. Euclidean is Galois invariant. So the theorem here is that there's a sort of spectral gap regarding these densities. So there's two constants between 0 and 1 such that this density is either 0 or 1, or it lies strictly away from 0 and strictly away from 1. So there's upper and lower bounds, and probably this interval is 1/12 4/5. Although I'll show you some stuff about computation in a moment. This is very hard to compute. There's this very simple argument that typically you expect the density to be 1/3. 1/3 of the Galois conjugate should be spherical. And it's important for the discussion that follows that we understand the cases of 0 density, where all the Galois conjugates are hyperbolic, and density 1, where they're all spherical. And we do understand those cases modulo a certain finite set of examples that have not yet been enumerated. So let me, rather than showing some details about the proof, let me just say the following. There's a lot of discussions where you want to understand how does a large finite subset of a torus distribute itself. Maybe it's rational points or something like that. And what often happens is that if you put delta masses on these finite points, that any limit of this sequence of measures is the uniform measure on a subtorus, or possibly on a union of finitely many translates of a subtorus. There's many instances in which that's true. This is one of them, this Galois invariant one. And that's an abstract theorem that applies very generally, but in this situation, to give a really concrete analysis and to prove this spectral gap, you have to figure out what are the possible exceptional tori that arise. Most sequences will uniformly distribute, but if they don't uniformly distribute, they'll give you some torus. And what torus is this? That turns out to be a very elementary geometric problem. And so I want to conclude the talk by sharing that problem with you. I call it the moving tablecloth problem. And it's one of the few things that I found very hard to put into a math paper, but very easy to demonstrate in public because it works best with a movie. So forget about the discussion. I mean, this has something to do with a torus, but think of this as a tablecloth where it has a square pattern on it, but it's changing in time. And yellow, we do not want to touch the yellow part of the tablecloth. Actually, we're willing to touch an edge of the yellow, but we don't want to go into the interior of the yellow. And what we want to do is take a small ball and roll it across the table so that it never enters the yellow. Okay, so you want to roll it across the table so it can touch the yellow, but it never enters the yellow. So does anyone see a way to do this? Yes, Dustin.
Let's go along a diagonal.
Go along the diagonal. Wow, look at that, because the yellow is never on the diagonal. Oh, wait, let me see. So you mean something like this?
Yeah.
Okay, yeah, that works. Good. Any other proposals?
The other diagonal.
The other diagonal, yeah. Generalize. Okay, fundamentally different. Okay, so notice that this line here that's running along the edge of the yellow, it sort of is continuously moving up, and then boing, it's still moving up actually, and then boing, it's still moving up. So if you always stay on that line, which is slowly moving up, you'll also avoid the yellow. So that's another solution. You see, you're staying on that moving horizontal line. And that's another, and that gives another exceptional torus. But the last one, which is rather tricky to find, is this one, where you jump from blue, just make it across. And then you go into light blue, and you just make it across, and so on. Okay, so this analysis is what underlies the theorem about about spectral gaps. So as an encore, let me just derive a few consequences. So for most triangle groups, the number of spherical and hyperbolic conjugates, the number of places where the group becomes spherical or hyperbolic, they're about the same. They're approximately agree within like a factor of about a third. As a corollary, you can prove in a simple abstract way this beautiful theorem of Takeuchi going back to the 1970s, there are only finitely many arithmetic triangle groups. And I'll say why in a second. But there's also a corollary, a much less well-known theorem going back to Waterman and McMullen that says there's only finitely many totally hyperbolic triangle groups. So let me just explain with two examples what these two words, arithmetic and hyperbolic, mean. So an arithmetic example, like 237, has the property that it's a hyperbolic triangle, but all its Galois conjugates are spherical. So there's only one that's hyperbolic. Okay, so in this case, the ramification density is large. It's 2/3, and there's only 3 conjugates, mostly spherical. The antipode of this is the totally hyperbolic case, and a really beautiful example is 142142. And for this example, all the Galois conjugates are hyperbolic. So its ramification and density is 0. None of its Galois conjugates are spherical. And these are very interesting to me because they're related to Hilbert modular surfaces. So we have a list of the 76 co-compact arithmetic triangle groups, which you can find in Takeuchi and McMullen Reed, all non-compact triangle groups with trace field Q are arithmetic. So this is done, and there's only 11 known totally hyperbolic triangle groups, but we don't know if this list is complete. And the last member of the list is this group I like very much, 142142. Why do I believe this list is complete? Well, there's some experimental evidence. So I checked that there are no other purely hyperbolic triangle groups with P, Q, and R less than 5,000. Now, if you think about all the triples of numbers where P, Q, and R are less than 5,000, that's about 1 billion. And then you have to take the greatest common divisor of those numbers. That's really big. And then you have to look at all the rational numbers with that denominator. And that's, basically 1 billion times 1 billion. And so there's a pretty big computation to sort of brute force check whether or not one of these triangles is purely hyperbolic. But I recently checked it in about 30 minutes using 5,000 cores running in parallel in Holyoke, Massachusetts. And what I discovered is that while mathematicians were sitting in their offices working on their iMacs, that the other scientists were building these enormous supercomputer centers, and I mean really enormous. This one is on a river so that it can use the hydroelectric power from the river to power the computers as well as cool the CPUs. And if you call the right phone number, you can get a login to this computer. And it was no problem parallelizing the computation, commandeering 5,000 cores and just running it all at the same time. And I should say that in a way I don't quite have time to describe, the algorithm can be greatly speeded up by randomizing it. And so I'm very confident that this conjecture is true, but I'm even more confident that there could be a much greater impact on mathematics by using the incredible computer resources that are secretly available on our campuses than by, say, ChatGPT. I think there's some really amazing computations which seem to be out of reach, which are now easily within reach. Okay. I don't have much time to tell you about the importance of this 142142 group, but one of its special features is it embeds in SL2 of its trace field, which has degree 6. That's not always true for a triangle group. And then from this embedding, you get a curve on a Hilbert modular 6-fold, And basically, that curve on the Hilbert modular sixfold shows that the theorem I proved for Hilbert modular surfaces does not generalize to all higher dimensions. But the only counterexample I could find was based on this very special triangle group, and it lives in dimension 6, not the next possible dimension 3. But what it shows is that the Jacobian is not enough information to explain why periodic billiard paths exist in all regular polygons. And here's a picture of, this is sort of a picture of the embedding into the Hilbert modular surface. I wanted to make everything very concrete. The universal cover of the Hilbert modular surface is a product of 6 disks, and the 6 Riemann mappings that send this quadrilateral to these various other quadrilaterals are the map that covers the inclusion of this curve V into the Hilbert modular surface. Okay, so there's a conjecture that this is the only group where such a construction is possible. And I just hope I've given you some idea of the really broad range of ideas and mathematical fields and discussions which flow from something as simple as the theory of billiards in a regular pentagon.
You wrote about something about Jacobians.
I'm not going to go back. It's 301. So there's some references that are included in the slides. But I don't want to quite conclude there, because this is mathematics at the crossroad of centuries. And I was thinking about it, and I realized I've known Maxime since before he was 28. That was back in the previous century. In fact, he was appointed as a full professor at Berkeley when he was 28. I was there as well. And I've also, I felt a sort of lack of nostalgia in this conference, because we haven't really looked back to the 20th century as much as I would have liked. So I just want to share this photo with you of me admiring the young, brilliant and very original mathematician that we're celebrating today. Okay, thank you.
Questions?
Yeah, this is Hodge theory in your title, and is it actually hypergeometric functions and
No.
related to this billiard group? No?
There is such a thing that can be discussed to the billiards group and also with the triangle group, but that's not the Hodge theory that I was alluding to. I was simply alluding to this idea of using the Hodge norm on the cohomology of an abelian variety with real multiplication as a kind of valuation on the cohomology when you have this K action. So that was the only place Hodge theory really entered.
But it's also the relations if you consider hypergeometric function.
Yeah.
And look.
Oh yes, of course. These actual maps.
Similar stories.
Absolutely. Yeah. Yeah. Absolutely. That's right.
More questions?
Yes, for the result about expressing every element in Q adjoining the golden ratio as a finite continued fraction with golden ratios attached. Is that result also true for 2 cos pi on n for other n's?
So it's true whenever the nth root of unity is of degree 4 over Q. So then the totally real subfield is quadratic. That's the key to the proof. Then you get to Hilbert modular surfaces. So that's why I was saying already for 7, there's a completely analogous thing where you use the fundamental unit in Q adjoin cosine 2 pi over 7. In place of the golden ratio, you try to form continued fractions, and nobody knows how to tell whether or not it's going to terminate. Yeah?
Can you tell us something about ergodic theory and dynamic billiard?
No, I did allude to uniform distribution, but the point of this talk was that not enough attention has been given to the periodic trajectories for these billiards, and they have a very rich structure which is related to some fundamental questions in thin groups and arithmetic groups. So that was really the focus. Yeah, Emmanuel.
Yeah, I wanted to know, is it known that you have only finitely many totally spherical triangles? So all the Galois orbits?
Yes. Let me just think for a second. No, sorry, that's not true. There's a line's worth of totally spherical triangles, And it's related to one of the places you could put a ball in that picture, which was like at the origin. So it's sort of a vertical line in this picture. So I should say there's a tiling of the universal cover of that torus is 3 space. And there's a tiling of that space by octahedra and tetrahedrons. And it's a really beautiful thing. You can build it with actual tiles. And the octahedra correspond to the hyperbolic ones, and the tetrahedra correspond to the spherical ones. And what you can find is sort of a chain of consecutive spherical polygons that contains an entire line. And every point on that line is Galois invariant, and every point on that line is totally spherical. But apart from that one line, which I had to find, there are only finitely many examples. And I think we know what they all are.
Yeah, just this curve coincide with the Shimura curve.
So the question was, does this curve correspond to a Shimura curve? I'm talking about something very simple. This is a line in Euclidean space. It's just a linear relation on 3 angles that forces all the triangles along that line to be spherical triangles.
No. But then you embed it into the, for example, H6 modulo delta.
Yeah, it doesn't have any embeddings into the hyperbolic plane because everything is spherical. All the corresponding embeddings would go into SO3, not SO21. So it gives a finite subgroup of a product of SO3s.
Okay, there are no more questions. I'd like to thank again.